Welcome back, everyone. Get ready for a deep dive that's literally out of this world. Today, we're tackling the chemistry happening in interstellar space.
Yeah, between the stars.
It might sound empty, but trust me, it's bursting with fascinating stuff.
Definitely not just an empty void. We'll be covering 5 key points today, starting with what interstellar chemistry actually is.
Then we'll jump into the sheer number of molecules floating around out there. It's mind-blowing.
Oh, and we can't forget about cosmic dust. What it is, what it's made of.
And of course, we have to talk about the insanely low temperatures.
Almost absolute zero.
Brrr. And finally, we'll explore the field that studies all this, astrochemistry.
Sounds like a plan.
All right, let's dive in. Now, when I think of space, I think vast emptiness, a vacuum. But you're telling me there are actual molecules out there.
Yeah, interstellar space isn't a perfect vacuum. It's incredibly sparse, which is actually great for scientists.
How so?
Well, it lets us study individual molecules without all the interference we get here on Earth.
Makes sense. So what kind of molecules can survive in that harsh environment?
Well, survive might not be the best word, but we've detected over 200 different types of molecules in interstellar space. It's pretty amazing.
200. Seriously.
Yep, everything from simple hydrogen and carbon monoxide to more complex organic molecules.
Like what? Give me an example.
Think sugars, even fullerenes, those buckyball molecules we talked about in our green chemistry deep dive, are out there.
Wow. Over 200 different molecules just floating between the stars. Okay, that is definitely cocktail party worthy. Now, you mentioned cosmic dust earlier. Is it anything like what I find under my couch?
Not quite. Cosmic dust is made up of teeny tiny particles, mostly silicates, which have silicon and oxygen and carbon. It's kind of like when we talked about nylon, remember?
Yeah, how those basic elements can create such different things. So this cosmic dust, it just floats around.
Well, it does more than that. These particles are basically the building blocks for planets and stars.
And maybe even life. Incredible. But, okay, picture this. I'm imagining these molecules and dust particles just hanging out in space. It has to be freezing out there, right?
You're not wrong. Interstellar space is unbelievably cold. We're talking close to absolute zero.
How cold is that, exactly?
Like negative 273.15 Celsius, or if you prefer Fahrenheit, negative 459.67.
It's hard to even imagine. I'm getting chills just thinking about it. How can anything happen at those temperatures? Wouldn't everything be frozen solid?
It's a good question. It's so cold that it does pose a big challenge to chemical reactions. Everything slows down. A lot.
So it's like the universe's super slow motion chemistry lab.
Pretty much. But here's the thing. There's a whole field dedicated to studying this. It's called astrochemistry.
Astrochemistry. That sounds so cool.
It is, and it involves some seriously impressive techniques.
I bet. We'll have to dig into that more.
Definitely. But first we need to remember that even though interstellar space is unbelievably cold and super sparse, it's not completely empty of energy.
Okay, interesting. So there's still some action happening out there.
Definitely. You've got faint radiation from stars, shock waves from supernovae, and even cosmic rays zipping around.
Wow, I never really thought about that. So even though it's weak, it's still enough to get things going.
Exactly. Those energy sources can be enough to trigger certain chemical reactions. Like, think of a cosmic game of billiards.
Ooh, I like that.
These little bits of energy are bumping into molecules, giving them the little push they need to react.
So even at those ridiculously low temperatures.
Things can still happen. And remember, we're talking about massive timescales here. Millions, billions of years.
True, true. So even if reactions are super slow.
Over that much time, they can make a big difference. Now, I know what you're thinking. How do we even study these reactions when they're happening millions of light years away?
You read my mind. We can't exactly send a probe to collect samples.
Nope. But remember those 200 plus molecules we talked about earlier? That's where things get really cool. Astrochemists use some incredibly sensitive telescopes, along with a technique called spectroscopy.
Spectroscopy. Okay, refresh my memory. How does that work again?
Basically, every molecule and element absorbs and emits light, but at very specific wavelengths.
Right, right.
It's like each one has its own unique fingerprint. So when astrochemists look at the light coming from a distant star, they can see which molecules are there based on their unique light signature.
So it's like deciphering a secret code hidden in starlight.
That's a great way to put it. And they can even figure out the temperature, density, and even how these molecules are moving just based on tiny shifts in those spectral lines. It's pretty incredible what you can learn from light that's been traveling for millions of years.
Mind-blowing. It's like we have a time machine letting us peek into the universe's history. But those incredibly low temperatures, that's still what gets me. I can't wrap my head around how molecules can react in those conditions.
No, it is hard to imagine, right? But think back to when we talked about cryo-EM, that technique for studying biological molecules at super low temperatures.
Right.
Same idea here. Yeah, most reactions slow way down when it's that cold, but they don't stop completely. And sometimes those low temperatures can actually help unique reactions happen that wouldn't happen otherwise.
So it's not just about what molecules are out there. It's about how they act and interact in this extreme environment.
Exactly. In fact, some scientists think that the extreme cold of interstellar space may have actually helped to create those complex organic molecules, the building blocks of life.
Oh, wow.
The idea is that these low temperatures can help stabilize those reactive molecules, keeping them from breaking apart too quickly. Think of it like a giant cosmic freezer preserving those molecules.
So maybe the extreme cold isn't a barrier to life, but actually where it all started.
Now that is a fascinating thought, isn't it? It's something that astrochemists are really digging into right now.
This has been so eye-opening. I used to think of interstellar space as this static, empty void. Now I'm picturing this dynamic environment with all sorts of chemical activity going on.
It is incredibly dynamic. Stars are forming, exploding, constantly ejecting material into space, and that constant change fuels the chemistry we're talking about.
Speaking of dynamic, earlier you mentioned something about astrochemists studying the atmospheres of distant planets. How does that tie into all this?
It's a great question, and it shows just how connected astrochemistry is to everything else. Remember those spectral fingerprints for molecules?
Uh-huh.
Well, astrochemists can use spectroscopy to study the atmospheres of planets orbiting other stars, those exoplanets.
So are they searching for those same molecular fingerprints, but in the light passing through the atmosphere of those distant planets?
Exactly. By analyzing that light, they can figure out what gases are present,
Which can tell us.
if that planet could possibly support life. For instance, finding oxygen, methane, water vapor, those are good hints that there might be something alive down there.
Like we're searching for the chemical fingerprints of life. That's so cool. But what about, toxic molecules? We talked about all those dangerous chemicals in our deep dive on toxins in neuroscience. Could there be toxic stuff out in space too?
That's a really interesting question. We know some molecules, like carbon monoxide, are toxic to us.
Right.
So it's totally possible there are other toxic molecules out there, maybe even some we've never encountered here on Earth.
That's a bit freaky, but also fascinating. I mean, could those toxic molecules tell us anything about life on other planets?
Absolutely. Finding certain toxic molecules might mean the conditions on a planet aren't right for life as we know it.
Makes sense.
But on the other hand, finding life that can handle those toxins, that could point to some totally new types of biochemistry.
Wow, it's like a cosmic game of hide and seek, with astrochemists as the detectives.
And the clues aren't just on those distant planets. Remember those complex organic molecules like sugars and fullerenes forming in interstellar clouds? Well, some scientists think those molecules might have been what brought the ingredients for life to early Earth.
So the stuff that makes life possible, it wasn't from Earth originally. It came from outer space.
It's a captivating thought. It really makes you think about how connected everything in the universe really is.
We are all made of stardust.
Literally. And that stardust is still out there, creating new stars, new planets, and who knows, maybe even new life forms.
This is incredible. I never realized how much was going on in that empty space between the stars.
And we've only scratched the surface. There's so much more to discover in this field. But now, let's talk about something really mind-boggling. Studying molecules at temperatures that are practically absolute zero.
Yeah, we touched on this with the whole cryo-EM thing, but I still don't get how scientists can recreate those insanely cold conditions here on Earth.
It does sound like science fiction, right? But it's real science. They use these super advanced techniques with lasers and magnetic fields.
Oh, wow. So what do those do?
Basically, they manipulate and slow down the molecules until they're just a fraction of a degree above absolute zero.
So they're basically making the coldest places in the universe right here in a lab.
Pretty much. And by doing that, they can see things that would be impossible to observe at normal temperatures. It's like hitting the pause button on those super fast reactions.
So what actually happens to those molecules when they get that cold? Do they just freeze in place?
Well, they do slow down a lot, almost like they're frozen. That lets scientists study their structure and how they behave in incredible detail, like looking at a snapshot of a chemical reaction frozen in time. But here's the really cool part.
What's that?
At those super low temperatures, they can see these quantum effects that are usually hidden because everything's moving too fast.
Quantum effects. That sounds complicated.
It is. Quantum mechanics is all about how matter behaves at the tiniest levels, the atomic level, and is full of weird stuff. But when things get ultra cold, those quantum effects become more obvious. It's like a whole new world opens up.
A glimpse into the bizarre world of quantum mechanics. I like it.
And those insights they get from these experiments, they're not just theoretical.
So it actually helps with
Understanding the chemistry happening in those super cold interstellar clouds, where things are working in ways we don't usually see.
It's amazing to think that the most extreme environments in the universe could hold the key to some of the biggest mysteries in science.
It just goes to show that science is all connected. Studying the universe on a huge scale can help us understand the smallest particles. So cool, right?
Absolutely. This deep dive into interstellar chemistry has been mind-blowing.
I'm glad you enjoyed it. It's a fascinating field.
And to our listeners, thanks for joining us on this journey. We hope you learned something new about the amazing world of interstellar chemistry. Keep looking up at those stars and remember that space between them isn't as empty as it looks. Until next time.